Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is a Voltech PM3000A universal power analyzer. It's a fairly nice instrument with a lot of capabilities. This is actually a 3-channel power analyzer. You can see channel 1, 2, and 3 shown here. And because of that, you can do analysis on 3 phases. And aside from doing basic power analysis, you can also do harmonic analysis, and it can give you a whole bunch of information about the nature of different loads that you connect to it. It also has a really wide dynamic range. You can see it goes all the way to 2000 volts peak and 200 amps peak, and you can capture those in fairly small spikes. So for example, for motor control or power on off, power on conditions of things, you can catch those events. And yeah, it looks nice. It has a little VFD display in the front. I've actually done power analyzer repairs in the past. I did a Fluke handheld one quite a while ago, but I've never done a 3-phase one. So we can take a look and see what it looks like on the inside and see the fault here in just a second. Now, fundamentally, a power analyzer is really nothing more than a 6-channel digitizer, because you have 3 channels here. You need to digitize voltage and current. So really, if you have a 6-channel oscilloscope, essentially, you can do all the algorithms on the waveforms coming from that. The challenge of these instruments is creating these channels to have a huge dynamic range and common mode rejection from each other, because you can have thousands of volts of different voltage between the 3 channels, and they have to be very well isolated from each other. Aside from them being isolated from each other, they also have to be completely isolated from all the digital circuitry that's in here, because after you do the analog to digital conversion, you cannot couple those directly to all the DSP that's built into here, and certainly not to the user interface, because you cannot have those voltages couple in. It can be lethal if something goes wrong. So this is going to be an exercise on really nice isolation techniques once we take a look inside and see how it is built. So let's go and turn it on. There we go. Let's see what happens. It takes a bit of time. There it is, and you can see all the lights turning on. So indeed, the processor is working. I think I just saw firmware version 2.2, and then it just says a voltage and current overload. You can see under the auto condition, both of here, we have reached 2000 volt peak and 200 amp peak. And of course, there's nothing connected to this right now, so it shouldn't show anything. So something's definitely wrong with it. I've tried all kind of buttons combinations, and really it doesn't do anything. Even if I go to 4-wire 3-phase mode here and go between the channels, absolutely nothing happens. I can turn the auto on and off. This goes away briefly, but then when I turn it back on, it comes back, and something's wrong with it. So we have to take a look and see what's going on. So let's go ahead and open it. Actually, before I open it, let me show you what's on the back, because that's where the inputs are. There's nothing in the front at all, and these are meant to sometimes be in racks and just connected to different instruments for analysis. Hopefully we can fix it, and then we can take a look at some power profiles and behaviors of some of the other things that are in the lab. And here's the look in the back of the unit. As you can see, we have 3 independent channels, 1, 2, and 3 for the 3-phase inputs. And by the way, this can go all the way down to DC, I believe, so it doesn't really have to be an AC signal, but of course it can go to a couple of hundred kilohertz as well. So here we also have a GPIB, parallel port, analog and alarms, output and inputs, and so on, and then RS-232. So it of course needs its own power. It doesn't take power from this. That would make things quite a bit more complicated, and all the digital stuff and all the DSP is going to run directly from that, and it's got some auxiliary inputs as well. So you can see we have voltage and current on each of these channels. So these are going to be independent channels. So I suspect that inside the instrument we would have different sections which are identical between these, and then this area here is probably all of the digital stuff. It's not that heavy, so I don't think there's too much in it, but it's worth taking a look at. There is also a digitization of the volt, can happen just simply by looking at the voltage across it. It's nothing unusual, and we're going to need a shunt resistor across here, and I assume this shunt resistor is going to be probably pretty small considering the amount of current that this thing can analyze. So after taking the cover off, there's another cover here for further isolation here. I'm going to try and remove this. Oh, there we go. And let's see, what do we have? And yeah, look at that. Looks very nice. So let me put this down and take a look here. I think I'm going to have to reposition the camera, but I can already see the different channels, as I mentioned exactly. You can see totally independent parallel boards here, and this boundary over here completely isolates all the high voltage input and the different digitization portion from all of the other digital parts over here. You can see some firmware there. I can see an EEPROM there, a different kind of processor. I can't see the main processor here, but it's probably this one right there. So yeah, let's take a look. So there's all these wires coming out, and these wires are coming from these 3 boards. You can see we've got some ferrite beads on each of these, and if I'm not mistaken, I believe that these actually carry the digitized data which means that there has to be some isolation. So this is probably either galvanically or optically or both isolated from this portion to this portion. That's quite a bit of design effort. Really, that's the magic of this instrument. Other than that, you can see is just take voltage and current, and there's the cat. There it goes. So you can take a voltage and current and each of these, digitize them and pass them forward. So fundamentally, there's really nothing going on other than that. But of course, all this engineering going into creating this high voltage isolation is the hard part. This is a massive, massive ribbon cable, by the way, that seems to come from the front panel. It almost seems like they've taken almost every button and passed it forward. Look at the size of this thing. So yeah, looks good. There's a power supply, main power supply, directly connected from the input. Looks like a little plastic garment here. Connected across this, and it's fairly loose. It's just power coming in, going in there, and then the rest of it is just isolated from there, and we have a nice ground connection. So let me put this on its side so we can look at it in the front and do some further analysis and see if we see anything obviously wrong with it. So let's take a closer look inside here, and it's interesting to see there's a little daughter board here that they've added afterwards. Various cables going around. These are just the analog channels, nothing unusual. The main power supply here. I checked the battery is still okay. We can see different processors and DSP units. There's some memory over here. It's probably to store all the digitized data before they're processed. I do see an AD16744JN. This is a 12-bit analog to digital converter, one channel, but I don't think this has anything to do with digitizing these. I would be shocked if that information is carried all the way here before it's digitized, and this is a single channel anyway. These need to be parallel samples, so there's certainly some other purpose here for that. We can see the controller for the VFD in the front, and the control for all the buttons and everything coming from the front panel. That's what all these ribbons are. Now, if you look carefully here, you can see the different wires coming from the front-end modules, and they have some beads on them, and I believe this is what's carrying pre-digitized data. There are some standoffs here, some standoff PCBs here, and these standoff PCBs could be doing some digitization. Again, I'd be surprised this is already too close. You wouldn't want that, and I'll show you some of these boards up there in just a second. So we'll have to do some reverse engineering and analysis, and I just noticed something as I was describing that. I don't know how well you can see it, but let me zoom in there. If you look over there, there's a capacitor right there next to these heat sinks, and this capacitor does not seem to be in very good health. It looks like it actually has leaked out. So that is definitely a problem. Now, this problem could be the cause of the failure, or it could just be something else that we need to pay attention to. So indeed, that needs to be looked at. So we'll have to do that afterwards. Now, the other thing is, if you look at these boards up here, you can see some familiar characteristics. So first thing is that the voltage is coming from the top. You can see again some beads under to get rid of some transient effects. And then we can see a piece of metal. That's our shunt resistor. You can see each channel has its own. Let me see if I can get that in view for you. Right there, you can see that those pieces, this guy right here. So this is probably about a milliohm or so. And of course, it's not precise. This is calibrated afterwards. So you can clearly see what's going on. We have the voltage going into this board, and then the current is sampled and sent through this cable over here into the board as well. And these boards themselves have two sections, one at the top and one at the bottom, and they're fully isolated from each other, just for multiple reasons, for protecting them from transient effects from each other, and of course being isolated from each other so that they don't spark to each other if you have a high voltage difference between those two ports. A lot of work has gone into engineering those. I think we're going to have to take one of those boards out just to make sure we really understand where the digitization happens in each of these. And if you look at the front here, on the front we can see we have quite a bit of isolation circuitry. You can clearly see we have optocouplers for sure. We have transformers. So we have galvanic and optical isolation, and it's possible that the data is sent through all of these for communicating back and forth, setting the ranging and all that. So certainly this is, I think, all the already digital data cables coming from there, and all the three channels are in parallel. Okay, looks good. So let's see, what should we do next? Well, there's a couple of avenues we can take. We can take one of these boards out, take a look at it, so we can do some reverse engineering on this and make sure we understand where the digitization happens. Given that it says overload on all three and all the channels at the same time, I am reluctant to say that the board is damaged. But it's not too difficult to swap two of these. In fact, I can take the cables from one channel, swap it, and just to make sure that the channel 1 and channel 2 are swapped, and we still see that error, so we can isolate that the problem is from this. And this capacitor here that was bad certainly has to be changed, so this board needs to come out, and we have to figure out how to do that. So first thing first, let's unplug these, swap two of them, make sure that doesn't change anything, and then we'll take it apart. Okay, I switched the cables. Let's give it a try again. and see if we see any difference at all, in case, for example, the channel 1 was the one that was not working. Now, I did that. There we go. I don't think it was plugged in very well. There we go. Now it's going to work. Same thing again, and nope, overload again. So yeah, something else is wrong. There is one other thing I can try. I can unplug the cables completely and then try it again. So basically not have these boards connected to the main part at all. So that would tell us something else. For example, if it would say a different error and it can't find the car, so we know at least there is some kind of communication. Let's try that. Okay, all 3 cables are out. So basically we have no connection whatsoever between this portion and this portion anymore. And let's see what it says now. No, you can see it still says that error. So something else is wrong. I'm fairly confident that the problem is with this portion. And that little capacitor there is in a critical place, probably some voltage regulators, something powering something else. And anyway, I hope that it hasn't caused a cascade failure. Alright, I went ahead and took everything out, and this was not easy. This instrument is not built for serviceability. It's just terrible. The whole entire chassis is basically sitting in ruins before I could take this out. So here's one of the channels, and we can actually connect this channel directly to here and power it on, because I also took out the power supply. And I think the power supply is okay, but we can do a quick test on it. So as you can see, this board is, essentially mostly through-hole. There's some conversion board here that has got some surface mount components, and there's a couple of unique and weird things on it, and I'll show you. So here's a portion that is appears to be problematic. This capacitor has certainly blown, actually. It's completely leaked out, and I'm wondering if it's even a short circuit. If it's a short circuit, that could explain the problem, because this entire portion is probably powered through these 2 regulators. And if there's no power to it and there's no communication, then that's the error, because even when I disconnect the cables, I get exactly the same error, and therefore this part may not even be powered because of this issue here. So hopefully it's a simple thing like that, and we can fix it. But I'm concerned is a cascade failure, as I said earlier. I still like to take a look at this anyway. So let's do one step at a time. Let's go take a close look here, identify these components, see how bad that capacitor is, and remove it, and look for a replacement. Here's something a little interesting here. You can see this, they've done this socket conversion here. So the footprint that's been on the board for this part is different from the package that they have. So they've built some kind of a converter, and this could not have been cheap. It's all done manually, most likely. That's one way to fix it. Either the part could not be found, or it was just the wrong one. And occasionally there are little surface mount daughter boards that they have made here just to compensate for some changes through the board, and perhaps some new components have become available. And these dip packages probably have been outdated, and that's the way they've gone around, so that they don't have to redesign the entire board. If it works, you don't have to change anything. So here's the section I worked on. I removed and replaced the capacitor. This is a 2200 microfarad 35 volt capacitor, and it replaces this 16 volt version of the same capacity. Now this one is open, and all the electrolyte has leaked out, and this thing essentially is an open circuit. It has almost no capacitance at all. So whatever functionality this was doing over here is gone as a result. Then I went to and looked at a little bit deeper into the architecture here and see what's going on. These are actually not voltage regulator as I originally thought. They are just PMOS, NMOS devices in an inverter configuration. The gate of them are being driven by this IC over here, which is an ICL7667 high power gate driver. So this IC converts logic TTL levels to gate level voltages that you can use to turn devices like these large powered devices on and off. So you can imagine that if this guy is, for example, an inverter powered from 12 volts, which is what's going on over here, I'll show you in a second, and then you modulate the gate voltages of these 2 devices, you can create some filtering at the output using this capacitor and generate some custom voltages. It's a very kind of a rudimentary PWM power supply section. At least that's what I think is going on here. I don't believe these devices are operating in an analog fashion, simply because if they were, you wouldn't be able to drive them with this IC. This IC even has I believe, a hysteresis control inside, and it's essentially a logic driver. So this section, therefore, may be tied to some custom power supply generation, voltage generation, which then ties into this circuit over here, which is the interface boards for the actual board that converts the voltages and the current measurements into a digital output. So this entire section can be severely affected if this capacitor is broken. Unfortunately, I can't test this until I put it back, and I don't even know if this is going to fix it, but we can do some measurements at least to get an idea to see what happens. If indeed what I described is what's going on, this guy being an open circuit with the previous one would certainly kill it. Now, I don't recommend what I've done here. The diameter of this capacitor is too large and it's touching the heatsink, and that's a really bad idea. I just don't have anything else to replace it. This capacitor would then run at a much higher temperature due to the heatsink being connected to it. I've created a thermal connection between these, so you can see the diameter of this was quite a bit smaller. And even themselves, they had put some tape on this so that there is no electrical contact as the metallic body of this. And this is, of course, already shielded, so I don't need to do that. So let's go ahead and take a look at the board itself. I've taken the cover off the board so we can take a closer look at it and analyze it a little bit more. And if you look over here, there's a lot of work has been done here for this to be isolated. Again, remember, all this is a digitizer, nothing more. It just converts voltages and current into digital stream, which can be processed by the board back there. So here's where the voltage comes in, and here's where the voltage across the shunt resistor comes in. Remember, these two sections can have a couple of thousand volts of difference potential between them. You can see isolation slots in the board as a result of that, to make sure that there is nothing arcing over. And this, of course, has a cover on it, which I've taken off, so it's even further insulated. Even these series resistors in the front have a little cover over them to prevent them from arcing. Some potentiometers here for adjustment, but essentially what's happening is that the signal is conditioned here using these various op-amp configurations. And then there is an ADS 7800 analog devices 12-bit A to D, which then converts everything into digital. So all this conditioning is to make sure you hit the right dynamic range, and auto ranging is done also here in this section by controlling the gain of the front end. After that, we have some other signal conditioning now in the digital domain. And then we isolate this entire section from the DSP board in the back. There's a couple of ways they do this. They do galvanic isolation using pulse transformers to send the data over. And then there is a series of Broadcom opto-isolators. These are gallium arsenide phosphide photo generation, or LEDs inside with photodetectors on the other side. And that creates isolation, nothing unusual. These are designed for specifically digital I/O replacements across two different power supply domains. So they are basically sending data this way and this way using the combination of galvanic and optical isolation, as we suspected when we were looking at the architecture from before. So other than that, there is really not much going on. These beads are, of course, because they're twisted pairs they've created for the pulse transformer link as well as the opto-isolator link. So that's all done quite nicely. So we can go ahead and put this back together and see if we can bring it back to life. Unfortunately, that's the only way to test it. Because I cannot have the display and everything else connected. Everything is just the cables are too short. This is not designed to be serviced. So now you can also understand what the role of these boards are, because what you have is data coming from the opto-isolators and those pulse transformers, and you need to convert them back into the digital I/O configuration for the rest of this board. And that's what these boards are doing. They're essentially just converting that. Interesting design here, where wherever there is a daughter board that's surface mount, everything else is through hole, probably an older design being kind of retrofitted. So let's do some quick measurements on this. I have the power supply here connected to my isolation transformer. We can turn it on and do some measurements to make sure that this inverter configuration I just talked about has at least some reasonable voltages on it, and that we can see activity on the gate of these devices. Let's give that a try. So I can go ahead and measure the inverter voltages. So you can see on one side this inverter configuration of 12.6. On the other side I have 0. And I can see some activity on the gates. Now I don't have the correct by ground reference here. I'm just using the ground from the power supply coming in, so it may be wrong, but at least I can see that indeed the filtering over here is doing something. A little tiny detail here that's interesting, worth looking at. This looks like a capacitor, but it's not. It's actually a standoff, and you can see that this is their way of attaching the chassis with a screw to this board while being completely isolated. So you have the entire dielectric breakdown of this piece of plastic here. This, I'm not sure what material it is. It kind of feels like Teflon, but of course it's not because it's black. But yeah, that's an interesting little detail that they had to put. The effort they have to go through to create an isolation between these boards is quite extensive. All right, let's give this thing one more try. So I haven't closed all the screws in case we need to open it again. Here we go. Let's hope for the best here. Okay, it's booting up again like before. And let's see. And yes, take a look at that. Check it out. Now it says 0 volts, 0 amps, 0 watts, of course. This guy is sitting at 0.2 amps pico. It's coming back down. Maybe needs some calibration. Anyway, this seems to be okay. Now the question is, what do we measure? Well, we can measure a couple of things around the lab. We can measure, let's say, some of these LED light bulbs, a few resistive loads, just so we can see what kind of analysis it can do. It should be fun to try it out. Okay, let's go ahead and do some testing here. And I thought maybe we would test something that has a somewhat surprising result. So up here I have my glue gun. This glue gun is very simple, only a few dollars. It's basically just for melting glue, and you can see the bottom portion of it. So I want to measure what kind of power factor, what kind of harmonic distortion this thing has. Now normally when you look at this, you would expect this to be just a pure resistive load, and these things can typically self-regulate themselves. As they get hotter, the actual power consumption can go down because the resistance of the heating element continues to go up. So let's go and measure and see what kind of thing could possibly be inside this simple glue gun. So right now everything is turned off. You can see everything is at the bottom. Before, when this was moving up and down a little bit, that was because I had forgotten to plug in the cable that was across the shunt resistor. So everything was floating on the current measure. That was my fault. There's actually nothing wrong with it. So let's go over here. Right now we're measuring 0 volts, 0 amps, 0 watts, and a 1 power factor. There's nothing there basically. So go ahead and turn on my isolation transformer here. And there it is. This is still not turned on, so you can see we have 117 volts here. This isolation transformer can go above the line coming into the house, or I'll just crank it up, and so we can put this device here a little bit under stress. There you go, 154 volts. Okay, we can go ahead and turn this on. Now, as soon as I turn on, first of all, note that here that everything is auto-ranging. As soon as I turn this on, we can say that initially it was consuming quite a lot of power, 200 and so milliamp, and it's going to continue to go down. But look at the power factor. The power factor is 0.677, which is unusual because you would think that it'd be resistive, so it'd be just 1. Now you can do all kind of interesting measurements on this. You can of course measure VA. You can see that this is 27 VA. You can do basic measurements like that. But what you can also do is look at the harmonics. So for example, the total harmonic distortion on the voltage is about 2.2%. That's essentially the noise of this instrument, really. It doesn't give you very accurate results below 2%. So yeah, so it doesn't really have that much distortion on the voltage line. But if I go under the amps, you can see that the amps THD is 73%, which is quite bad, meaning that there's a lot of harmonic being present on the current that this instrument, this component here is actually consuming. We can look at that. We can go under A harmonics, and we can select which harmonic we want to look at. So I'm going to look at the second harmonic, press enter here, and you can see that the fundamental harmonic is drawing 99 milliamp, whereas the second harmonic is 40 milliamp, and you can see the difference between the phase of those two. So indeed it is producing a fairly poor current waveform, and you can see the different phases of the various harmonics. So why is that? That's because this thing actually has a triac inside, and some of the power control is done by a triac. I cannot adjust anything. This only has a power on and off, so you're going to get a better look at it. So really, this kind of device in here, this triac in here, is going to create a weird waveform. So this is not a simple resistive components anymore, which is, I think, quite interesting. And you can also do other things like looking at the peak current that is consumed. You can see here's a peak voltage that came in. Here's a peak current when it was turned on initially, so it stores all of that as well, which I think is nice. So this is really working, and it's a very powerful instrument, especially if you start using it in 3 phases. It can give you efficiency, it can help you measure transformers and all kind of different things. The GPIB port in the back can be hooked up to a software, and then you can do graphing and plotting and storing everything and grabbing the information directly from this. So yeah, it's a nice instrument. It was certainly worth fixing. I'm sorry that the repair wasn't that exciting, but sometimes it is what it is. And again, I want to thank my Patreon supporters. You're the reason why these things are possible. I have a whole bunch of other equipment in the queue to do. I have a whole bunch of reviews I need to do, just really limited by time. So let me know what you think in the comment section, and let me know what kind of repairs you want to see in the future. I have a kind of wide variety of instruments here. Oh, I'll see you in the comment section.